Imagine trying to predict exactly how a bridge vibrates during a storm when you have the blueprints for the bridge, but absolutely no sensors measuring the wind. We often face this tension between knowing the physics of a system and being blind to the external forces driving it. Today, we explore a framework that solves this by mathematically embedding those unknown forces directly into our physical models. To understand why this matters, consider the gap between theory and reality. Traditional engineering relies on differential equations that assume we know every input affecting the system, but in the real world, driving forces like wind gusts or internal friction are often unmeasured. This limitation breaks our trusted models exactly when we need them most. This is where the Gaussian process latent force model offers a breakthrough. Instead of guessing the force, this framework represents the unknown input as a Gaussian process, a flexible statistical tool. It effectively fuses the rigid, interpretable structure of physics with the expressive, uncertainty-aware nature of machine learning. The elegance of this method lies in how it handles the math. We convert the statistical prior of the force into a stochastic differential equation, allowing us to stack the force's variables right on top of the physical variables in our system. Once combined, we can use standard tools like Kalman filters to solve for both the system state and the mystery force simultaneously. Now that we understand the mechanism, let's look at how we configure these models and how well they actually perform. The success of this approach depends heavily on choosing the right kernel, which describes how the force behaves over time. We use matern kernels for standard physical forces that change smoothly, but we can switch to periodic kernels to capture vibrations in rotating machinery, or exponential kernels to detect sudden, abrupt impacts. In practice, these models are powering the next generation of digital twins and virtual sensors. For example, in wind turbine studies, this method achieved strain estimation correlations between 0.96 and 0.99, proving it can accurately reconstruct what is happening inside a system, even without direct measurements. By admitting what we don't know and modeling it with precision, we can build systems that are robust to the chaos of the real world. To learn more, visit emergentmind.com.